Hello everyone. So now that we're done with chapter 1, we're going to move into chapter 3. And then after 3, we're going to go back to chapter 2 and then followed by 4 and 5 for the remainder of the semester. The reason why we're skipping over 2 and going straight into 3 is because you're going to learn about evaluating properties and finding information in tables and how to calculate specific numbers and states that you'll need for the first law of thermodynamics. And the first law of thermodynamics is covered in chapter 2. So this is a pretty long chapter. It's a lot of information, and it's information that you are going to be using all semester long and then also into Thermo 2. This is probably going to be one of the longer lectures, or maybe not even in terms of length, but in how much tedious detail you will have all jam-packed into one chapter. I'm going to try and spread out chapter 2 because that one is also an extremely large and cumbersome chapter to cover. It's the biggest chapter of the entire semester, so I'm going to try and devote a lot of time for that, as much as we can. So this one, just kind of bear with me, and it's a long lecture, but it is a good one. Okay. So properties are extensive or intensive. Remember, intensive I is independent of mass size and extensive is dependent. And it's defined as characteristics of the system to which you can assign a numerical value. So here are some. We've got pressure, temperature, specific volume, enthalpy, and internal energy. And then all of these you can and will be assigning a numerical value to. So the state is the condition of a system or substance that is defined by its properties. So those extensive or intensive properties define numerically the condition of a system or a substance, which by then gives it a state and a name. So in a given state, all properties of a system are fixed. So that's how you'll be able to assign a numerical value to them. And then if a system exhibits the same values of its properties at two different times, the state is the same at those times and is therefore a steady state. So here are 3 different states. So it's the same substance. So right here we've got water. Let's just say water. At 30 degrees Fahrenheit, so right below freezing, it's a solid. And then at 40 degrees Fahrenheit, it's a liquid. And then 212, it's a vapor. So all of these are still water. They're all H2O, but they're existing in 3 different states, right? So you've got a solid, a liquid, and a vapor. So one thing to note is that's kind of how I want you to remember the change in states. But if you have the same properties, so the same properties that make this a liquid at 2 different times, so say you are, heating this up or whatever, and it's not changing to vapor, it's staying the same, that means that you have a steady state. So if these don't change and it's always a liquid, then you have a steady state. A process is the transformation from one state to another. So for example, when we went from that solid, let's see if I can back up. Okay, when I went from the solid to the liquid, this was a process right here. When I went from the liquid to a vapor, this is a process. So it is the change from one state to another. And when the properties of a system change, the state changes. So that makes sense, right? Because these properties right here have the numerical value. These properties are what is determining the state right here. Okay, so this solid right here has a bunch of different properties. And that's what's defining them. So if all of these properties change, the state's going to change, right? So if all of these properties change to this, then the state is going to change to this, and you will then have a process. Okay, but remember, we did say that we were able to have a steady state right here, where all of these properties and everything like that are the same at two different times. We do have certain properties within those to remain the same. And that can be constant pressure, constant temperature, and constant volume, isochloric, thermal, and baric. And then cycle is when a system at an initial state goes through a series of different states and finally returns to the initial one. So not the same thing as steady state, right? Because if this was steady state, say we started at initial 1, if it was steady state, all of these would need to be 1, right? Because it never changes at two different times. It's not the same thing as cycle. So we've got 1 and 1 and 1 and 1. But cycle is when it goes through multiple different and then comes right back around to 1. And then if it does it one time, that is called one cycle. And if you do it multiple times, then you know that it is cyclic. Okay, pure substances. These are substances with no chemical reaction taking place, and they are homogeneous. So we have a couple of different reactions and energies. Right now, we are only going to focus on pure substances in this class. And within this class, we're going to consider water and air, things like that, to be pure substances. And these pure substances can exist in more than one state. We just saw that water can be solid, liquid, vapor. Here's a couple of other examples. So let's look at water in a piston cylinder. And let's look at 5 different state changes, right? So right here we have, over here on the left, we've got state 1, which is subcooled or compressed liquid. Those are the same thing. Subcooled means compressed liquid and vice versa. What is our subject of analysis right here? It is water. We've got our pressure of 1 atmospheric and then a temperature of 20 degrees Celsius, and we see that it's got some heat. Right now we know that pressure is constant. Why? Because atmospheric pressure and the weight of the piston are unchanging. Okay, so this piston right here is not changing, and the atmospheric pressure is not changing. Okay, so we know that that's constant, but we see this heat down here. So if we know that the heat is steadily being applied, then we know that it's going to increase. Okay, so we've got the state 1. We're going to go, this is a process right here, to state 2. Saturated liquid, about to vaporize. So here, again, pressure is constant. Why? Because atmospheric pressure is still 1, and the weight of the piston is unchanged. The only thing that is different here, right, is the temperature was increasing. Temperature is constant. This is something that I want you all to kind of look at in a different way. So when we go through the next couple of state changes within this, this is when you're talking about water heating up, right? Because we're heating up water, and it getting to a point of vapor. So when you are boiling water at home, if you left the lid off and you had a little bit of water in there and you heat it up to a point to where it can vaporize, which is 100 degrees Celsius, right? It's the boiling point. That's where we're at now at T saturated. We know that once you hit 100 degrees Celsius, it's not going to bam evaporate, right? It's not going to turn into vapor. It takes time. It's not something that happens immediately. So within that, we are going to look at these state changes as that changes. And that's why our temperature is constant. Our temperature is going to stay constant until all of our liquid changes to vapor, because that's what we're concerned about. right? Okay. So T is constant. Temperature stays constant during this phase change. And T saturated equals 100 degrees Celsius, boiling point of water. Okay, so let's go to state 3. We've got a two-phase mixture right here. So none of this can escape. Like if we were boiling a pot, some of this would be able to escape. It's all staying in here, and we see that this water has now turned into liquid, which is, well, has remained liquid, but some of it has turned into vapor. So we've got a two-phase mixture right here. Same pressure, constant. Temperature is constant because we know that until all of this liquid has turned into vapor, we're going to stay at 100 degrees Celsius because we are looking at the change in that. And we know that it's not just immediate. And then V, as more heat is transferred, part of the saturated liquid vaporizes, right? So that we understand that. And then we're going to go straight to state 4, saturated vapor. So now we have gotten pretty much all of it to, this is the point to where it's all turning into vapor. So P is still constant, T is constant until it's completely done, and V increases. And then we go to state 5, which is superheated vapor, where pressure is constant, temperature is at 300 degrees now, we're at a superheated vapor, and let's look at this on a PVT surface so that you can kind of see how this works as well. So here's a PVT surface. Obviously it's pressure, specific volume, and temperature. I'm just going to refer to specific volume as V. So again, this is for pure, simple, compressible systems. Pressure can be determined as a function of temperature and specific volume. The graph is in relation for water, and then also it shows values of pressure, specific volume, temperature at equilibrium location. This is something that's in your book that you will have, but we're going to look at it in depth and plot them on here. And so obviously this is PVT, but if you were to take it and put it into a 2D schematic, you would have a TV and a PV diagram. Okay, so right here, let's see if I can get my cursor. Okay, so you could have a TV or a PV. And so if you look at it from two different sides, that's where you would get the TV or the PV. So this is the TV column with that example that we just had where it started off at 20 degrees Celsius and then came up to 100 degrees Celsius. Here's that constant time where we were in that liquid vapor region. Remember? So right here, we were at liquid, we had water, we heated it up, got to that boiling point, and then we looked at all those processes and states all in here when we had the liquid and vapor until we got to the point to where we were all vapor, and then we went straight up, and this should be the 300. And this is that superheated vapor, right? So this is that line that we were working on. Okay, and then you've also got a PV, which does the same thing, but it's pressure and volume. Okay, so here's some definitions of some terms. TSAT, which is saturation temperature, is the temperature at which vaporization takes place at the given pressure. Same thing for PSAT, pressure at which vaporization takes place at the temperature. So it's just referencing its other. Saturated liquid, pure substance that exists as a liquid at TSAT and PSAT. Same thing for saturated vapor at TSAT and PSAT. Critical point is the point at which saturated liquid and saturated vapor states are the same. We also have PCR, which is critical pressure, and TCR, which is critical temperature, found in table 1. We are going to look at all of these tables now. Subcooled, we know that that's the same thing as compressed liquid. And that's if the liquid temperature is less than Tsat at Psat, right here. And then if the liquid temperature is greater than Psat at Tsat, got this. And then superheated vapor, which we knew when we got, that was our state 5. And if you notice, here's our state 1, and here's our state 5. If the vapor temperature is greater than the saturation temperature at the given Psat, here it is, and then the same for Tsat, okay? So here's the terms on that PV and TV diagram. So we've got the critical point right here, okay? We've got the compressed liquid zone. So remember that example that we had where we started off at water. We know that it's the compressed liquid zone. And then we moved up, 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 up. This constant line of pressure. So we moved up the line of pressure. Here's our T. So we're moving up in temperature. We were given that liquid heat. And then bam, we've got a constant bar and a constant temperature, right? So this was when we got to that boiling point, 100 degrees Celsius. We knew that from then also that V was increasing, remember? So we've got V increasing, increasing, increasing. We're in our 2-phase mixture, our liquid and our vapor phase. So we have some liquid and we have some vapor, and we're trying to get it all to vapor. We're still giving it, the V is increasing, but our T is the same until it's all done, until the very last drop of that water is vaporized. And then bam, back up to the heat, because we're giving it heat, giving it heat. And that's when we get into the superheated vapor zone, okay? And so on here also, this is our saturated liquid line, and then this is our saturated vapor line. And then this is a critical point just right in the middle. And these dotted lines, this actually isn't in the book, but I thought that that would help you kind of understand. I mean, this isn't a firm start and stop, but it's just a good visual. And then we've got the same thing on the PV, but do you see where we have, it's in 2D and then we just reference for the PVT. So if you've got the TV, we reference the P, and that's these constant lines, the isobars. Same thing for the PV. So we just reference the bars, but these are isotemp. Okay, so lines of constant temperature. And then this is lines of constant pressure. Okay, simple compressible systems. The change in volume is very high. So I want you to understand that the change in volume is very high for this. Makes sense. And then, but that's in comparison to other reactions, right? So surface magnetic and electrical effects are negligible. These are for pure substances. They're described by intensive properties. And for a simple compressible system, 2 independent intensive properties are needed to determine the state. For compressed subcooled liquid or a superheated vapor, P and T are 2 intensive independent properties. So that makes sense because we were plotting them on that line and determining their state. 2 notions that are important inside the dome or the curve, you'll hear me refer to this either way. P and T are dependent, okay? So in here, in this 2-phase mixture, because everything underneath the dome is 2-phase, in this 2-phase mixture, P and T are dependent. Outside, P and T are independent. Okay, so that's 2 really important things to understand. 2-phase mixtures are under the curve, inside the dome. P and T are dependent intensive properties, and therefore we need a 3rd intensive property to determine the state. Whereas the data, we can use graphical tables, which is what we will end up using, and then empirical equations. Empirical equations and these tables are put into software nowadays, but the software is really expensive. I won't say that it's not widely known, but it's not the most accessible software to get, or sometimes even user-friendly. So this is why we focus on the tables and knowing at a minimum where to use these, because you'll find that once you get the hang of it, they're really easy to navigate. Okay, so one thing that I want to look at is this point of we need a third intensive property to determine the state. So, but we just plotted them, right? We're talking about under the curve, and that's because P and T are dependent. So we don't know where that is in there, where the state is on that line underneath the dome. So here's our example again. So state 1, subcooled or compressed liquid, P is constant, T increases. So we know that. Let's look at that on this diagram. So we've got a T, V, we've got our dome, we've got our two-phase mixture. We know that under the dome it's two-phase. We've got everything labeled, and we've got the bar. So at state 1, right here, we know that going from state 1 to state 2, that temp is going to increase. So we're going up to increase in temperature, but pressure is constant. Lines of constant pressure. So we know that we're going to stay on this line. Here, state 2, saturated liquid. Makes sense. Look, we got to this saturated liquid line. This is where we know that we are. So we get here. Pressure is what? Pressure is constant. We're going to stay on this constant line of pressure. T is constant. We're about to go into here and look at this line. This line is not increasing. We're not going up in temperature after 2. We're staying constant right here. Tsat, which is 100 degrees Celsius. So we know where that is. And then two-phase mixture is state 3. So we're getting into here into the two-phase mixture. We're still on this isobar. We know that P is constant. We're at the same temperature. Temperature is constant, but V is increasing. So here's V. We're increasing in V. Okay? And then we go to 4, which is saturated vapor. Right here, we're on the saturated vapor line. Okay? What is P? Constant. We're still on this line. What is T? Constant. We haven't done anything. We're still here. What is V? We've still increased. Okay? And then to state 5, P is constant. We are still on this line. We're still here. What is T? Increasing. So we're at about 300 degrees Celsius here and 20 degrees Celsius here. Doesn't seem like I drew that pretty to scale, but anyway, so this would be 300 degrees Celsius and this would be 20 degrees Celsius. Somehow that would work. But what I want to talk about is why you need a third property to determine where this state 3 is. So what did that say exactly? It said under the curve, so in the two-phase mixture, P and T are dependent. Okay, so pressure and temperature are dependent. Makes sense? This is constant, this is constant. Intensive properties, and therefore we need a third intensive property to determine the state. This is because state 3, right here, we only know that it's going to be on this line and at this temperature. That's all we know from the given properties. So why can't it be right here? Right here, right next to 2, it can be constant pressure right here. It can be the same temperature. Why can't it be right here next to 4? It can be constant pressure right there. It can be the same temperature. It doesn't have to be 3. It doesn't have to be right in the middle, given the data that we have. Because right now it could be anywhere on this line and still be the same thing, given the data that we know. So that's why we need a third one. We need something else to tell us where in that line we are, okay? We just know that V is increasing, but we don't know where it is. We don't know where on this line is. So that's why we need the third property when we're talking about being under the dome. Because 1, we know where it is. 2, we know where it is. 4, we know where it is. 5, we know where it is. But when we start getting to where we're using inside the dome, we don't know where it is. And that's what we need to find. So here it is again. I just explained this. So it's 3 is not fully defined. We know that we need a third intensive property. So this shows you again, this is your 100 sat or T-sat, 100 degrees Celsius. These show you your processes right here. 1, 2, 3, 4. There you go. You've got processes in between your different phases. And again, this dot right here can just be anywhere. Okay, so here's some table notes. I think it's at the end of chapter 14. It's at the end of the book are all of these tables, but I think directly after chapter 14. Here's the tables that we are going to use. The water tables are 2 through 5. They're all related to water, and we call these the steam tables. 2 and 3 deal with everything inside the dome, so two-phase mixtures, or the saturation table, that's 2 and 3. A4 deal with the superheated region, vapor, and A4 deals with compressed, subcooled, or water liquid. A2 are all properties, specific volume, internal energy, enthalpy, entropy, and they're all intensive properties. And a way that you can know that is that it's all divided by the mass. And then subscript F, which you'll see, designates the property of a saturated liquid. And then subscript G designates the property of a saturated vapor. So when you'll see those, just remember that F is for saturated liquid and G is for saturated vapor. And then just another note, A2, and all of the students miss this, so be sure to highlight it or maybe even like stick a sticky note right above this column. It's the only column, but it's under specific volume, the saturated liquid line. It must be divided by 1,000. And you'll see that it's the whole page of the note, and there's all the numerical values. And whatever numerical value you pick up from this one particular column, it's the only column, it must be divided by 1,000. And it says it there really small at the bottom. So please do not miss this. So let's do an example of the tables. Right now, let's just do, and feel free to pause this and get your book or get your tables out so that you can follow along with it. These tables, there's a lot of them, and they're not particularly difficult to navigate, but it is going to take some practice for you to get comfortable with them. And the best way to do that is just to get them out and start using them. And you are going to use them a lot. So the better and more comfortable you get with using them, the better for you. Okay, so H2O at saturated liquid state, temperature is 20 degrees Celsius. We need to find pressure and specific volume. So right here, I've already put out the solution. That way you can come back and look at it. But let's look at, let's see. Oops. Okay. So I've got the table right here. Okay. So right here, here's all of your tables. We know that it's a saturated H2O. So we know that right here, saturated water, and we're looking for water at saturated liquid state right here. So we know that we need to go to A2, which is exactly what it says. So let's scroll down to A2. Okay, here's A2. We know that T is 20 degrees Celsius. Here's our temperature. So let's just come right on down to 20 degrees Celsius right here. So here is our specific volume right here. It's in meters cubed over kilograms, and then we know that it's a saturated liquid, right? Because they just told us this, water at saturated liquid. So we know that we need to go to the saturated liquid, not this saturated vapor. You see VF, because F denotes the saturated liquid. You see G right here, that's the saturated vapor. This is that column that I'm telling you guys about. Do you see right down here? It's the table value divided by 1,000. It's the only column, so make sure that you understand that and that you remember that every time you pick up a value from here. So right here, this specific volume is right here, 1.0018 divided by 1,000. So that's what we've got right here, and it's, don't forget your units, meters cubed, kilogram. I also denoted pretty much everything more than what was asked. So here's the pressure right here, 0.02339 bar, because it's pressure in bar. And then we've got internal energy, and it is right here. Internal energy, we've got saturated saturated liquid. UF, again, it's denoted by F, and it's kilojoules over kilogram. So you'll just come down to our temperature, pick up this number. What else do we have? Enthalpy right here, saturated liquid, will come down to 20, 83.96. And then entropy, saturated liquid again, come down to 20.2966. Okay, so that's a really easy one. Let's go ahead and do the next one. Okay, and so we've got water again at saturated liquid state. We know, okay, saturated water, we're good here. Temperature, 33 degrees Celsius. Okay, scroll down to 33 degrees Celsius. We need to find pressure and specific volume. So here's our pressure, 0.05034 bar. Specific volume, this is Vg, though. The one that we had before was V subscript F. So we are looking for the saturated vapor within the specific volume. So we've got specific volume, V subscript G at 33 degrees Celsius. And then that's saturated vapor. So we'll come down, 33 degrees, saturated vapor, 28.011. Hey everyone, I just realized that I made a mistake when I was going through and reviewing this. This should have said saturated vapor state right here for your second example, saturated vapor state, and you know that because your specific volume, your G denotes what state you're in. So if this was liquid, this would be F, just like the example that you just saw. But because this is saturated vapor, you know that you need to denote it with a G. Okay. All right. And of course, meters cubed kilogram. Right. Let's see. Okay. So what was the question? So we did both of these and then draw a TV diagram and specify all the given values. So we know that we found both of these, and now let's put it on the TV. So we know that 20 degrees Celsius is our TSAT, and then 33 degrees Celsius is our additional TSAT. This is how you can end up with multiple lines of constant pressure, right? We've got our critical point right here, our VF. Let's look up here where we found that. Right here, VF, specific volume, saturated liquid. This is where we got that. We know that the saturated liquid, that's on that saturated liquid line right here. Okay. And right here, that's where it's noted down. on our V. And then we did the same thing right here, but with VG, because we know that that's on that saturated vapor line. Remember, we used the two different columns within the specific volume. We had both the saturated liquid and the saturated vapor. So that's kind of how those are ended up plotted and what those mean on here. Okay, so this is a PT diagram, whereas we have been using TV and PV. You can do a PT. It's a common way to show phases of a substance, and it helps out a little bit, especially because a lot of them are constant. So it helps to show the phases on here, but it is shown a little bit different and it has a few different characteristics. So here's the PT. We've got sublimation, vaporization, and fusion. We've got it, remember our water sample or our water example where we went from a solid to a liquid to a vapor, right? So all of this can be water. We can exist in all three of those. And then instead of a critical point right here, we have a triple point. And that's where all of them exist in equilibrium, right? The liquid and vapor are in equilibrium, but also the solid. I'm not sure why I didn't put that in. But that's the critical point. All three phases are in equilibrium. Sorry about that. The critical point up here, obviously, is when the liquid and vapor exist in equilibrium. And then vaporization, liquid to water, fusion, solid to a liquid, and then sublimation, solid to a vapor. So just when those, in our example, when we went from a solid to a liquid, this is where it would have gone over that fusion. And then from that liquid to a vapor, it would have gone over that vaporization. Okay. And then same thing. This is substances that expand on freezing water, and then substances that contract on freezing water. And this is not a linear. This is kind of like a little arch, but that's the big difference between these, other than the pressure, obviously, because we're talking about expanding and contracting on freezing water. Okay, here's another example that we'll do. This is not water. In your tables, mostly what you will be seeing, especially at first, is water, but they do have other things like this refrigerant R134A. So let's look at this. Let's see. Okay. And again, all of these examples within this lecture will have solutions, and it will really give you detailed instructions on how to get it at first, but by the end, you should be able to get through to them. And then I will also be posting a review for an assignment coming up, and you will have an assignment before your test coming up, and your test is going to cover chapters 1 and 3. Okay, so how do we know where to go, right? Because we're not sure what state it's in. Before, when we had an example, it told us what it was in. It told us that we were in a saturated vapor, so we knew to come to A2. But we don't really know where we start, because we could start in any of the phases. So as engineers, you always have to start with an assumption. So we start with the assumption that everything is a two-phase mixture. And then what we do is we go in and verify and rule out things and eliminate things and hone in on what that state is. So we start with the two-phase mixture, which is table A10. Oops. Okay. There it is. Okay, yep, This is it. Some of the tables go more than one page because the temperatures, they have more than fit on one page. So we go to table A10. We've got a temperature of 20 degrees Celsius. That's what I was looking to make sure was on here, and it is. We've got PSAT, which is 5.716 bar, okay? And then it says below that, because the given 1.4 and the table is showing 5.7, this is a red flag that we are not using the correct table. So if this was a two-phase mixture, then our T and P bar should be the same, right? Because we should be at the same table. So we know because we're using the two-phase mixture, table A10, for R134A, we know that at temperature 20 degrees Celsius, we have a PSAT of 5.716 bar, way different than 1.4. So we know, hey, this is not the right table. We are not in the right place here. How do we get to the right place? There's a flow chart from that. And this is why we always assume a two-phase mixture, because if it's not, then we have a path to go on to figure out where that is. So here is, let me get to this flow chart. This is the given flow chart that you'll be able to use. And you just start with the question. So here, start with saturated liquid tables. Okay. And then right here is at the given T, is P equal to PSAT? Well, no, we know that, right? At the given T at 20 degrees Celsius is P 1.4 equal to PSAT 5.76? The answer is no. Okay, if it was yes, we'd come down here, but it's no. So we're going to come over here. What's the next question? Well, at the given T, is P lower than PSAT? Okay, so here's P 1.4. Is that lower than our PSAT 5.716? Yes. So let's come over here. Now we know superheated vapor. Use superheat tables. Okay, now we know where to go. So when you're looking for a state, start with your two-phase mixture and answer your questions. Come down here, find what you can answer. If it's yes, then you come down here. If it's no, then you come over here and you answer another question. If the answer was no, it would have been a compressed liquid. So it brings you all the way over here to help you get what you need to do. And just a note, in this document, Y represents any of the following. So it's in here what you can use. And it even tells you right here, we're using pure substances. We know that. That's all we're using in this class. Here's some pure substance inclusions. Here we're using R134A, so we know that we can use this table for this. And here are the tables that you'll be able to use. So, okay, so we figured out that we need to go to superheated vapor, use superheat tables. Okay, well, then let's go to those tables. So we're right here at table 10. Okay, here's our properties of superheated R134A vapor. Okay, our P-bar right here is 1.4, so we need to be using this. Come to the 20 degrees, right over here, and we've got 0.16520 right here, because that's what we're looking for. Specific volume, and it's meters cubed. Okay, so make sure that you're picking up that correct pressure bar, because there's a bunch of them. Don't get in a hurry and just pick up the first one. All right, and now let's plot that right here on a PV. So we've got temperature at 20 degrees Celsius. We've got V, we just found that, 0.16520 meters cubed over kilogram. And then we've got a pressure of 1.4 bar. Okay, here's another example. Again, what are we going to do? We're going to start with a two-phase mixture. We're at water. We know that that's A2. We just came off that. Oops. Okay. Temperature is 300. Okay. 300 degrees Celsius. Pressure of 150. What's our pressure right here? 85.81. That's not really looking like we're in the right spot. Okay. So let's go straight to our flow chart. Okay. So let's look. At the given T, is P equal to P sat? No, our P sat is 85.81 at table 2. But it says that our given is 150. So no, that's not right. So let's go to no. And then, okay, well, at given T, is P less than P sat? Is 150 less than 85.81? No. Okay. Oh, compressed liquid. Okay, I'm loving this. Are compressed liquid tables available? Yes, they are. Let's use them. Okay. 85. And you might be thinking, hey, why does it say are compressed liquid tables available? We're using them. Because not all of the substances, compressed liquid tables are available here for water, but not for all of them. And there's a whole nother way to get to that if they're not provided. Okay, so let's find our 300 right here. Okay, we're at it. But gosh, this is 150. Is that where we're supposed to be at? Yes, it is. Okay, so pressure of 150, temperature of 300 degrees Celsius. What do we got? Here's our V, 1.3770 meters cubed kilogram. And then what do we need? U, 16.6. What is that? Kilojoules over kilogram. I put a lowercase j, so I'm going to go ahead and correct that so that you guys have it for your notes. Okay, and then here we are, we just put them on the PV diagram, right? So 150 bars our pressure, temperatures 300 degrees Celsius, because right here it's a PV diagram, so we know that this is a line of constant temp, okay? So we're plotting that pressure. And then here's our V, of course. Okay. Quality. So let me make this bigger for you guys. Okay. Quality, denoted by a lowercase x, is the ratio of the mass of vapor present to the total mass of the mixture. So that's a really fancy way of saying how much vapor you have in your mixture. And it's undefined if we do not have a two-phase mixture, which means that we must be under the dome for quality to exist. If you are outside the dome, quality does not exist. And the quality property is used to assist in finding the location on the line in a two-phase mixture, and it is an intensive property. So remember when I said, hey, this state 3 can be anywhere because we know that it's a constant temperature and a constant pressure. We don't know where at it is underneath this dome because all of the data that we have only tells us that it's constant temperature and constant pressure. It doesn't tell us anything else. This is where quality comes in. This is why it only exists underneath the dome. So here's a formula, but it's really simple. See, quality of 0.7 is 70% vapor, 30% liquid, so I've just plotted that here. A quality of 0 is 0% vapor, 100% liquid, so that would be here. And then quality of 1 is 100% vapor, 0% liquid, so I've noted that here. So X just denotes the amount of the amount of vapor. So if you have an X of 0.8, we know that you have 80% vapor. If you have an X of 0.2, you know that you have 20% vapor. let me save those changes that I had written up. Okay, two-phase mixture formulas with quality. Here are some of the formulas, but basically V is less than V liquid, VF, V is in between VF and VG, and then V is less than VG. And then here are those formulas for specific volume, energy, and enthalpy. And then also these can only be applied to any specific property in the book, but only to phase mixtures, right? Because you're not going to apply anything that has to do with quality, denoted by an X, in anything other than a two-phase mixture, because everything under the dome is a two-phase mixture, and that's the only place that quality exists. And here's a representation of that two-phase mixture. So let's go ahead and do an example for the specific volume, internal energy, and enthalpy of R134A. And it's at a temperature of 70 degrees Celsius and a quality of 0.6, which we know is 60% vapor. So here again is the solution, and we're just going to be using these formulas that was found on the previous slide. So here, remember I gave you the formulas. So we're just going to be using these. So again, what do we start with? We always start with the two-phase mixture assumption. Okay, and in this situation, we know that it's going to be two-phase, right? Because it gives us a quality of 0.6. So that should go to show you why having a third intensive property is very important, because it tells you more information about the state of the substance that you have. And so it's great, you know, they gave us a third intensive property, quality. We know exactly what it is. It's two-phase mixture. So let's go to that table. Let me see if I can make this. Okay, so A10, let's go to A10, 9, 9, 11. Okay, a little too far. Okay, here it is. So A10, 134A, liquid and vapor, right? So at a T of 70, right here, let me move this up so that you guys can see it. 21.162 bar right here. And then VF right here. Remember this one, this table is the one that is divided by 1,000. So we've got 1.0027 or times 10 to the negative 3. You can do either or. And then VG is the next one over, 0.0086 meters cubed per kilogram. And then we know that the quality is 0.6. So then what we're going to do, now that we have everything that we need, we're just going to plug in and then calculate. And so we get specific volume, internal energy, and enthalpy. And then, of course, we want to know, we've been using these tables to find all of these temperatures at 70 degrees or 80 degrees or, 10 degrees Celsius, whatever. But we know that in a real world situation, we're never going to have exactly 70 degrees Celsius, right? We're going to have, what if we have 72 degrees? What if we have 75? What if we have 71.5? What if we have 70.001? So you can have all different types, or you can have all different temperatures depending on the situation that you're working. And so how we find the data that's in between those data sets, right? So we know 70 and we know 80. How can we find what's in between there? And that's where linear interpolation comes in. And I know that some of you are just like so happy to see this again. I know that quite possibly one of you, this is your favorite thing. So don't worry, there's a lot of examples, and it's really quite easy. It's not a difficult one, so not a lot of the interpolation that you're used to. So we know that this is used to fill in unknown gaps between two known values. So if we know that 70 degrees Celsius and we know that 80 degrees Celsius, we can use linear interpolation to find everything in between. So here's an example, water temperature of 200 degrees Celsius, specific volume 0.4 meters cubed kilogram. We need to find P. Again, assume a two-phase mixture. We're going to solve it just like normal. So let's go to A2 because we know that that's water and that's our two-phase mixture. You're going to be starting with A2 a lot because that's the two-phase water mixture and we just use it a lot. So let's see. There it is. Okay. So within this, we know that we're given a T of 200 degrees Celsius. So here it is. And then we are going to find specific volume saturated liquid, VF. We know that F is liquid, G is vapor. So come down to 200. We've got 1.1565, and then we divide that by 1,000 or multiply that by 10 to the negative 3. And then the vapor, specific volume saturated vapor, VG, 0.1274. And then we're given this V as well, specific volume, 0.4. So we're going to go to our flow chart to verify, right? So down here, we've been previously using a pressure at a given temperature, but in this situation, we're actually looking for P, right? So here, find P. So we can't use P if we don't know what P is. But here we have at a given temperature or a given pressure is YF liquid less than your given Y, and then less than your given vapor. And then this Y is just substituted for what you have been given. Right here, we've given a specific volume of 0.4. So let's look at that. Y of F, which is our V of F, 1.156, is that less than 0.4? No. And then is our V, 0.4, less than YG, which is our VG? So is VF less than 0.4? No. And is 0.4 less than VG? No. So we know that the answer is no, so we go over. So we're going to come over here because the answer is no. And again, right here in this document, Y represents any of the following: U, V, H, or S. We're given V, specific volume. So right here, at a given temperature or pressure, is Y greater than Y of G, the vapor? So we're going to come over here. What is our Y that's given? 0.4. Is it greater than VG, 0.1274? The answer is yes. So let's come over here. We need to go to the superheated vapor tables. And so let's do that. That is A4. There is another one thing that I do want to highlight. You actually see a different, it's not so much a flow chart, but it's just a document that tells you where the tables are that you need to use. But this one is a lot easier to use in my opinion because it walks you through the steps that you need to take to get there. So that's why we use this one. But I am going to go ahead and post that other document, and feel free to play around with it, but I will not be using it. What we need to do here is we need to go to our given temperature, but we're looking for P, and there's a ton of different pressures. They've got 0.7 bar, 1 bar, 1.5, and another page with more. And what we need to do is we actually need to narrow down. So we need to narrow down these available specific volumes and get as close as we can to what we know, which is 0.4. So let's just pick one, 0.1, and see if we can find this 0.4 in our specific volume, because that's what our V is. Don't make sure that you're not looking over here. So we've got a bunch, nothing. It's really helping us out here. Okay. Let's keep going. We want to narrow that window, right? So we don't want a huge a huge difference. We want to get as close as we can. We want to box in that 0.4 as close as we can to make our interpolation a lot easier. So let's come up here, 200. Well, 0.429, that's really close to 0.4. Obviously, you see 0.4 here. That's a different temperature, so make sure you're picking up the correct temperature. 0.4, and then 0.2999. That's really close. Okay, so we know that 0.4 is in between this 0.4249 and 0.2999. So we know that it is somewhere in between 5 and 7. And you see that the bars, this pressure is what's driving these tables. And then the data within it just helps you find what your pressure is. So this is where I'm saying, hey, you're not going to be given all of the data, right? So we're given a table for a pressure of 5 and for a pressure of 7. And we now know that by looking at our given temperature of 200, if we know that what we're looking for is specific volume of 0.4, and right here at 5 bar, it's 0.4249, and then at 7 bar, it's 0.2999. Well, then we know that by proxy, our pressure is going to be somewhere in between 5 and 7. So therefore, we're going to pick up this data and use our interpolation to find what that pressure is. And here's the formula that you'll be using. Again, well, I've noted what each is, but you'll see that Y is just like what you are using on an XY axis. So right here, V is going to be your X, that's your given. You'll put in, this is your VA right here, which is your lower limit, your VC, which is what you're looking for, and then your XB is your upper limit in regard to your pressure, right? So this represents a pressure of 5, this represents the pressure that we're looking for, and this represents the pressure of 7. So that's what I mean by lower limit, because we're looking for pressure. So I'm referencing pressure. So then what you do is I highly recommend you just set up your equation like this, or your information that you know like this, so that you can plug it into the equation up here, and then you just solve it. It's really easy. And here we just rounded it. Okay, let's look at a bigger example. So suppose that 0.136 kilograms of water is contained in a vertical cylinder piston arrangement as a two-phase mixture at 50 degrees Celsius. Initially, the volume beneath the 113.4 kilogram piston, which also gives us the area, is 0.03 meters cubed, with the atmospheric pressure of 101.325 kilopascals, gravity of the constant 9.14 meters per second squared. The piston is resting on the stops. So at all of that information, the piston is still resting on the stops. Energy is transferred to the arrangement until the piston rises from the stops. What is the temperature of the water when the piston first rises from the set of stops? And then we'll show the process on a TV and PV diagram. So let's go with what we know. First of all, right off the bat, we're using a cylinder piston arrangement. We know that it's a closed system, right? That's the example that we've been using pretty much all semester long. We know that mass is not transferring in between, but we do know that energy is transferring in between. So we know that this is a closed system. What else do we know about this mass? We know that it's constant. What is this volume? The volume is also constant because it's a rigid tank. Anytime that you see rigid tank, volume is constant. Highlight this, you'll need to know. We know that it's a water substance, and we know that it's a two-phase mixture. What do we know about how this arrangement or how this example is working? Well, first of all, what does it say about what the piston is doing? The piston is resting on the stops. So in all of the other examples, we didn't have stops, but the piston is at rest. The system is at rest, and it's not moving up and down. And we know that by the sum of forces, that piston is at equilibrium. All of the forces up equal all of the forces down. But that's not what's happening right now. What's happening right now is that this piston's resting on the stop. So we know that there's not enough force internal to it to make it rise or not need to rest on those stops. Okay, and what are we looking for? We're looking for what the temperature of the water is when the piston first starts to rise from the sets. So here's the example continued. Here's state 1. Here's all the forces down, and here's all your forces up. And even the stops are providing a force, especially at state 1, because the piston is resting on it. And here again, the pressure here is not the same as equilibrium pressure because the stops are providing the upward pressure as well. If it was an equilibrium pressure, then these stops would not be providing any force. They would not be used. It would be as if they were not there and this piston would not move. Here's a schematic of state 2. And then we see that it's just now at equilibrium, right? Because we don't need anything. And then at state 3, that's when it first starts to rise. So even though this shows it already risen, this is just the point that it first starts to rise. And what are we looking for? We're looking for temperature at state 3. So state 1, your mass is 0.136 kilograms. That's given. Your specific volume is 0.03 meters cubed, or total volume, sorry, is 0.03 meters cubed. Mass of the piston is given, pressure atmospheric is given, temperature is given, okay? And then right here, we've got specific volume at 1. Here you go, we can find that. All you're gonna do is take your total mass right here and divide it, total volume and divide it by your mass to get your, right here, to get your specific volume, because we know that when something is specific, it's divided by the mass. Temperature at 1 is 50 degrees Celsius, and we need to find that P1. So what can we do? We can go to that table. Okay, so let's go to table A2. So this is kind of an all-encompassing example of what we have learned thus far. Okay. 50 degrees Celsius. Here's our pressure, 0.1235. Okay, so our PSAT is 0.1235. So let's continue. We've got our state 1. Now we need to find our state 2. So again, this is the state that it is just about to move. It has not moved yet, and what we want to know is the point at which it starts to move. So the state 2 is at the point that it is just about to move. We're not needing these stops at this point. So we now need to reach an equilibrium pressure, right? So where all of the pressure here is able to push up this piston if we were to increase it. And how do we find this? We can do the sum of forces in the y direction, right? Because the y is going up or down. So here we just do the sum of forces, pressure atmospheric times area of the piston, all going in a downward motion, minus, because we're also still going in a downward motion for the piston. So mass of the piston times gravity, which is the constant 9.14. And then what is going up? Right here we've got pressure. And then that's P2 times area of the piston because it's being applied to the piston. And then here we're just isolating what we need to find, things like that, solving through, and right here. And so it's when we reach this point, the piston will start to move. So at this point, if we add anything to it, any amount of pressure, the piston will move. So this is on the cusp of movement. So from state 1 to state 2, it's a constant volume, because we know that, rigid tank, constant volume, and isocort constant. Okay, let's continue this. Okay, state 3. This is what we're looking for. We know that specific volume is equal 1 to 2. We know that the specific volume is constant, isocort constant, right? 0.22 meters cubed kilogram. We know that P2's bar is 10.30 bar. We just found that out. We know that that is the cusp of movement. T2, what is T2? We need to go to the tables, okay? Okay, let's see, A3. Why are we going to A3? We're going to A3 because it's a two-phase mixture and we're assuming the two-phase mixture. But we need a pressure bar of 10. Right here, we've got our pressure bar of 10. We've got a specific volume. Whoops. Saturated liquid, VF, 1.1273. We know that that's multiplied by 10 to the negative 3 or divided by 1,000. We know that the vapor portion of specific volume, Vg, is 0.1944 meters cubed per kilogram. And again, we need to use the flow chart. We need to use the y. We need to plug in our v's because that's what we're given for the y's. So at t or p is yf less than y and is y less than vg. We know that we can use our v in place of the y. So at t, at a t or p, so what are we given? We're given pressure. So at p is vf, right here, 1.127, less than our v, which is 0.22? No. And is our v, 0.22, less than our vg, 0.1944? No. So we know that this answer is no. We're going to come over here. And at t or p, we're given p. Is v, 0.22, greater than vg? Yes. So we're going to go to superheated tables, which is A4. Okay, and we know that right here, in the previous example, we didn't know what pressure was. So we were kind of trying to backdoor it into a pressure, but right now what we're looking for is temperature. So this is a lot easier. We need to go to the 10 bar of pressure. Let's keep going. Right here, and we're looking for the temperature. So here's a bunch of temperatures. And we're given V, so let's just find where it is in between those. So let's write down what we know. Well, our known is 0.22, so let's find where that is. Okay, we've got 0.2270. We know that it's less than that, and the figure that is less than that is at 200 degrees Celsius. 0.2060 is less than 0.22, and 0.22 is less than 0.2275. So we know that it's in between 200 degrees Celsius and 240 degrees Celsius. We know that these are our limits that we're looking for. Remember, our limits before were pressure, because that's what we were looking for. Now our limits are temperature. That's what we're looking for, and that's what I'll be referring to. So when you set this up, you've got a V of 0.2060 meters cubed per kilogram equals 200 degrees Celsius. That's our lower limit in reference to temperature. And then what we're looking for is in between here, 0.22, which is given, and we're looking for the T. And then what is our upper limit? 0.2275, which is 240 degrees Celsius. That's our upper limit. Then you can go back and do the same thing that I did here. Right? This is why it's easy to set it up this way, because then you can just plug in these values and write them just like I did. So then we're going to plug them in right here, and then we interpolate. Here's the formula with our given, and here's our temperature. 226 degrees Celsius. So we know that 226 is in between 200 and 240. All right, so we've got the answer at state 3. Okay, so I know that that looks like a lot, and it is, but when you break it all down, you really start to understand how everything works. And so when you go to use your flowcharts and your tables and your formulas and things like that, come back through this first and work through these and get really comfortable with how to navigate this. And when you see that you're looking for something, how to go and find that. Even if you have to make your own little cheat sheet, like, hey, step 1, step 2, step 3, things like that. That's a really good thing to do, because you see that it took me 3 slides to solve this in a very condensed manner. So let's move on to ideal gas. It's also known as perfect gas. Ideal gases have very low density. Here's some examples. And these only use the ideal gas laws, okay? So when you have a question where we've been getting water, H2O, well, we know that, water is water and we can use water tables. Well, when you see an example and it's giving you air or oxygen or nitrogen, I need that to clue you into I can only use the ideal gas law. So this ideal gas law is also known as the equation of state. We usually use the one that's PV equals MRT, but there are other variants, and I would like you to use whichever formula fits what you've been given, so that you can solve it the quickest. So again, PV equals MRT. R is a constant. It's a specific gas constant. And then R equals R bar over mass. And then there's PV equals nRT. R bar is a universal gas constant that is determined by which units that you use. So R bar equals 8.3145 kilojoules over kilomole Kelvin. And then EE is 1545 feet pound force over pound mole Rankine. And then N equals mass over molecular mass. And then N is the number of kilomoles of gas. PV equals RT is specific volume equals total volume over molecular mass. And the whole thing is meters cubed over kilograms, which is SI units on a mass base. And then PV bar equals R bar, T equals specific volume bar equals molecular mass times specific volume. All of that is in EE units on a mole basis, with that molecular mass being kilograms over kilomoles, and then the volume being meters cubed over kilograms. And then also to find the molecular mass, M, values are in A1 and A1E, dependent on which units you are using. And then you can find R from the values in 3.1, and that's in chapter 3. So right here we have a tank with a total volume of 15 feet cubed, and it contains a mass of 20 pound, so pound mass, of an ideal gas with a molecular mass of 24 pound mass over pound mole, and a temperature of 80 degrees Celsius. Find P. So the first thing that I want you to clue into is, whoa, this is an ideal gas. I can use an ideal gas law. The second thing that I want you to notice is that we're in EE units, and that there's something here that is not in EE units, which is obviously the first thing that you should notice is the Celsius. So you should be seeing now that these things are not all homogeneous, and that we're going to need to be doing some unit conversions within this. So let's go ahead and start with our ideal gas law. It's PV equals MRT. We are looking for P, so let's just pass on that. We do have total volume that's given to us. We do have mass that's given to us. We were not given R, but we can find R with the given information. And then we are also given T. So let's find that R. We've got R bar equals R over molecular mass. We know that R is a constant. We just went over that, 1545 feet pound force over pound mole Rankine. And then we're going to divide that by our molecular mass that's given, which is 24 pound mass over pound mole, which gives us 64.375 feet pound force pound mass Rankine. And then we know that we need to get that temperature to EE units. So we're going to get it to Rankine, which is your Celsius plus a constant of 459, which is going to give us a 540 Rankine. And then we're just going to plug in from there. So we're going to isolate P. And when we do that, we're going to move total volume over. So instead of PV equals MRT, it's going to be P equals MRT divided by total volume. We're just going to plug in from there. Again, we need to get these to homogeneous units, and we need to do a little conversion here at the end, 15 times 1 foot cubed over 12 inches cubed. And then we end up with a P of 321.88 pound force over inch squared. So this one's pretty easy because we've been given all of the information, and we can just use that constant in EE units. But what if we don't have an ideal gas? So for ideal gases, PV bar equals R over R bar T equals 1, but for real non-ideal gases, it deviates from 1. And this deviation from 1 is called the compressibility factor, Z. And therefore, P V bar over R bar T equals Z. And to find these values of Z, we can use the compressibility charts, which are in appendices figure A1, A2, A3, figure 3.12 in chapter 3. And then also this generalization, compressibility charts are applicable to all gases. And then PR is reduced pressure, TR is reduced temperature, and then PC and TC are the critical points found in table 1. And actually, let me see, should still have these up. Table 1, yep, okay. And so we see we've got TC and PC here. And yeah, and there's a denotion of one of the critical points here. So let's do one of these examples. We've got sulfur dioxide, a pressure of 35 megapascals and a temperature of 450 Kelvin. We need to find specific volume and molar specific volume using the ideal gas law, equation of state, and the compressibility chart. Okay, so let's start with P V bar equals RT. V bar equals RT over P, because we're just isolating, right? So it says that we need to find this. So we're going to get it on a molar specific volume, which is denoted by the bar across. We're going to use this constant for SI units, right? That should be up here. Yep. So remember, R bar for the molecular, which is denoted by the R above it or the bar above it. And see, this bar right here for this V is for mole bases, and then without it is for mass bases. But we know that we have a constant of 8.3145 kilojoules over kilomole Kelvin. So let's come back here and just plug that R in there because it's a constant. We're in the right units for Kelvin, so we're just going to plug in temperature, and then all of that over our pressure, which is 35 megapascals, but we need to get it into kilopascals. And so we need to do 35 times 10 cubed kilopascals. So from there, we can get our specific volume on a mole basis, V bar, equals 0.1069 meters cubed kilomole. And then we can do V bar equals M molecular mass. We plug this meters cubed kilomole that we just found over what we need to do for our mass right here. And where do we get this? Where do we get molecular mass? We get it from the tables. Let's see right here. Okay. Okay, and right here we have, Sulfur dioxide, 64.06. That's our molecular mass. So we can just plug that in here and then just multiply across. So we've got 1.668 times 10 to the negative 3 meters cubed over kilograms. And then we can do PR equals P over PC to get that critical pressure. And that equals, what is our P? It's 35 megapascals. So 35 times 10 to the third to get that unit conversion. And then that's over PC. So where can we find PC again? From the chart. So let's just bring that up really quick. What is PC? Sulfur dioxide, 78.7 right here. So we can do 78.7. Of course, we need to get homogeneous units to get it to kilopascals. And then that ends up with 4.447. And then we can do the same thing for reduced temperature, T over TC. We know what T is, 450 Kelvin. But where can we get this critical temperature? Back from the tables again. So let's go right back here. TC, 431 Kelvin. And then you get 1.044. And then we can use the chart to find Z is about 0.6. So how do we find that Z is about 0.6? So we go to those charts and let's see. Let's go down. Compressibility factor. This is at the end of that very long attachment where we've been using A2 tables, for specific heat or super vapor tables, two-phase mixture, things like that. If you scroll all the way down, you'll start getting into these charts. And here are the generalized compressibility charts. So we're going to come down to find Z. We are looking for, let's see, this one. Okay. Yeah, so we've got 4 here. And let me see if I can zoom in. Okay. Okay. So right here, what we have, the reason why we're using this table is because we have a reduced temperature of 1.044. And so right here, we've got a reduced temperature of 1 and then a reduced temperature of 1.05. So we know that it's about 1.055. So we're going to have to follow one of these lines because these are our constant temperature lines. And so let's just go ahead and say, well, it's pretty much 1.05 because we're at 1.044. So let's follow this line up. And we need to get to 4 because our reduced pressure right here, reduced pressure is 4.44. This is 4, this is 5. So we're about right here. And then here so that we can see this side. And then we're looking for the Z, which is on this line. Okay, so what we're going to do is we're going to follow this 1.5 all the way. You can see it actually converges with this reduced temperature line of 1. So be very careful when you're following these lines. We're going to go to about 4.5, and then we're just going to pull it over to the side. Let's see if we can see this. Yep, okay. So 1.05, we're going to follow until we get to about 4.5. Really, we're 4.447. And then we're just going to bring it over to the side to find our Z. And where it converges is really close to about 0.6. So we're saying, that's why it's not equals, it's just about 0.6. And how do we know that this is not an ideal gas from a Z equals 0.6? Because right up here, if it deviates from 1, It is a non-ideal gas. So that's not all that it's asking. We have found the Z, and it's 0.6. We know that it's not an ideal gas. This is when we can go back and remember, on a mole basis, PV over RT equals Z. And so what it did ask for is find the specific volume and molar specific volume, the ideal gas law, and the compressibility chart. So this is the ideal gas law. Now we're using the compressibility chart, and we still need to find the specific volume and the molar specific volume. So here, we're just going to isolate the specific volume on a mole basis, plug in what we know, and then this is what we get on a mole basis. And then we know that we can take that and divide it by the molecular mass to get specific volume. And then we'll just plug in and get our specific volume there on a mass basis as well. So you can use either of these equations to decide if it's or to find out if it's an ideal gas or not. Or you can use a series of tests and you can use either or test. You don't have to do them both, but we will do them both just for the example. But you can use one of the two or both really quick tests. Students tend to prefer the test method a lot more than adding some equations onto it to find out if it's an ideal gas law. So these tests are, you have two options. So it's if your reduced pressure is much less than 1, we're talking like less than 0.01. And from our example, we know that PR equals P over PC, and we know that P is greater than PC. So we know that our P, which is 35 times 10 to the third for that conversion, is much higher than our PC, which was 78.7 times 2 for that conversion. So we know that this is way higher. We've got a way higher numerator than we do a denominator. So therefore, we're not going to have a PR that is much less than 0.01. And so we know that this test has failed. You don't have to do both options. If this test fails, this test is going to fail. But if you're working off a temperature, you can do a very similar thing. The other option is if your reduced temperature is greater than 2 and it is not near the critical point. So from our example, we know that the reduced temperature is T over TC. We know that our T is higher than TC. And with this one, you do have to look at the numbers and do some calculating in your head. But when you look at it, you know that your T is 430. You know that your TC is 431. You know that you're going to be right around 1 something. Either way it goes, you're not going to be over 2. And you know that from looking at your numbers, that your TC is 431, which is nowhere near your critical point. So thus this fails the test as well. So you can do all of those, the equations, they'll only take you, if you do them a couple times, they'll only take you a few minutes to add on. So you can either do that if you're more comfortable, or you can use these options to decide and verify if it's an ideal gas or not. Okay, so this is the lecture portion of Chapter 3. Also be having a test that is going to cover Chapter 1 and Chapter 3, and you will get a review on that as well. Okay, thank you.